In this lecture, I will introduce the basics of wireless communication. When discussing wireless communication, there are a variety of different standards that may come to mind. There are a variety of different technologies that may come to mind. But wireless communication is the sending of various signals within the electromagnetic spectrum over the air. And these signals are present all around us in our modern day world, from the Wi-Fi that we may have in our homes or in office buildings, cellular phone signals as we travel throughout the world, amateur radio. Some people still communicate over ham radio setups that they may have in their backyard or in their vehicle, AM/FM radio broadcasts, satellite broadcasts, television, and more. So there are various frequency bands assigned to different technologies, and it's very important, if you are going to work at all within wireless communications, that you understand the different frequency bands and how they're allocated. If you start broadcasting within a frequency that is assigned to someone else, you can very quickly get in a lot of legal trouble. And the FCC, which is part of the federal government, tightly regulates the use of different frequencies, and this allows us to have public access to a variety of different data channels operating at different frequencies without interference. So for example, if you were a broadcast television studio and you wanted to broadcast over a particular channel, you wouldn't want somebody else in the parking lot or somebody else across town also broadcasting at that same frequency, because then when viewers try to tune in to your television channel, they would get interference and have another signal come in. And so that television studios, television broadcast channel company pays a lot of money to be able to have access to that particular frequency. AM and FM radio stations are the same way, and so if you are broadcasting at a particular frequency, you have paid for the rights to be able to operate at that frequency, and so you need to ensure that no one else is operating at that frequency. And so typically what you may notice on an FM dial as you're going from one channel to the next is that it ranges from 88 to 108 megahertz, and typically each of the stations that you would tune into in the United States has a decimal and an odd number. So you might have 93.3, 93.5, and this allows enough spacing between frequencies that you don't have interference with nearby channel numbers. And typically within a region, those stations are assigned far enough apart that you generally will not have two stations within 0.2 megahertz of one another. In larger cities, you may see some crowded frequency bands, but typically they are still spread far enough apart that you don't see interference. If you click on these links here, they show the allocation of these different frequencies. So I will temporarily pause the PowerPoint and show you this first link here, which comes from the NTIA, and what this shows are the different frequencies and what they're assigned to. So it's important to note that all of the broadcast frequencies are within the radio spectrum. So here you see the broader electromagnetic spectrum, which ranges from very low frequencies all the way up beyond visible light, all the way up through cosmic rays. And the useful frequencies for radio broadcasts are within this bandwidth in here. So from about 3 kilohertz up to 300 gigahertz. And various different uses are assigned to the different frequencies. So you can click on this link and explore, but they're basically allocated into different categories. So for example, broadcast television is in this frequency band here. You may also see amateur radio is in this frequency band here and also over there. And you can see the colors are assigned to different categories, from amateur radio to professional broadcast, some other things for space communication, for mobile phones, and aeronautical navigation communication, those kind of things. So you can see how each spectrum, each frequency range within the spectrum is allocated to very specific uses. And so you would not want to have an FM broadcast station outside of 88 to 108 megahertz, because radios would not be designed to pick up that frequency. This is also important to note that this is the frequency band within the United States. So other countries have their own standards. So for example, I was traveling to Japan several years back, and their FM broadcast in some parts overlaps the 88 to 108 megahertz that we have in the United States, but I was able to pick up some Japanese stations and not some others because I brought an American-made radio. And so that particular radio was designed for US broadcast and would not work for accessing all FM stations in another country. So just be aware that these different frequencies are assigned to different purposes. Let me get back to my PowerPoint and we will continue here. The second link that I have is from the FCC, and this is just a table format that showcases all of the different frequencies that are in there. Now, one important event happened in 2009. After many years of analog television broadcast, the FCC tried to reclaim, and in fact did reclaim, certain frequencies within the spectrum for other purposes. And that was the so-called shift to digital, or transition to digital. And what that meant was, if you had an older television set or had an older antenna that was designed to receive signals from the frequency bands that were formerly used for radio or for television broadcast over the air, you needed a conversion kit. And these were available at a lot of electronic stores in the later part of the first decade of the 2000s. And that allowed you to receive over the air the signals from the newer frequencies that could still interface with your television through a converter box. Now, in that transition, there were some things that were gained and some things that were lost. So one thing that happens is lower frequency signals tend to propagate longer distances, and higher frequency signals can transmit more data in the same time frame. And so what that means is you can hear an AM station much further out than you can an FM station. But typically AM stations are used for things like talk radio, sometimes sports broadcasts, and they don't have the fidelity that the FM stations do. You cannot really have a high quality sound over an AM radio broadcast compared to what you can send over an FM broadcast. But the FM station dies out after a certain distance away from the tower, whereas an AM station can possibly, on a clear night, be heard from several hundred miles away. This also means that if you have a new wireless router in your home that operates at dual band frequencies of 2.4 gigahertz and 5 gigahertz, the 5 gigahertz channel can send data faster across the network, but it does not propagate as far. And so if you have a larger home, you may take advantage of the 2.4 gigahertz to be able to access your network from the farther reaching points of the house. But if you are within range of the router and can still get the 5 gigahertz, that will give you a faster data transfer speed. What that meant for the transition to digital television was that the frequency ranges assigned now for broadcast television shifted to a higher frequency. And so that meant that you could now send high definition signals over the air, and you could send them with much clarity and much data, but you could not send them as far without having a powered antenna to receive them. And so I can remember growing up in the DC metro area, I could, as a child at my parents' home, receive television broadcasts from the Washington, D.C. area and also from the Baltimore area, just with regular rabbit ears on a television set. And once the transition was made, we could no longer, on the same antenna, well, certainly not with the same antenna, but even just with a converter box and the antenna, receive the stations from Baltimore. Now, with powered antennas, at my parents' house, you can once again receive the Baltimore stations. But because they were being sent at a higher frequency, we were able to get high definition over the air, but we were not able to get things as far. And so my father had a place on the top of a mountain that was probably about an hour and a half outside of the DC metro region. And when I was a child, we could take a television set out there and just set up the rabbit ears and pick that up from a far range. But now you cannot get very good television at all without having a higher powered antenna that is not just passively receiving those signals. And so there's some good and some bad of higher frequency. And so if you want something that can go a long way, lower frequency is better, but you cannot put as much data in that broadcast, and so that precludes being able to use some of the higher fidelity signals that you might want to broadcast for music and television. Antenna size is also very important. So you may wonder, why is it that some things have really long antennas and some things have really short antennas? Well, the reason for that is that antennas are the length that they are based upon the wavelengths of the signals that they are receiving. And so if you have a citizens band radio antenna, they are 102 inches long, and with that size antenna you can pick up frequencies approximately 27 megahertz. Those are much longer than you need to pick up an FM signal, and you might see an FM antenna on a car. A lot of times, modern day cars, those antennas are now much shorter and in a shark fin or a stubby type configuration, but for a long time you saw an antenna that was maybe about 3 feet long coming out of a car, about 2 feet long, and those are designed to pick up frequencies between 88 and 108 megahertz. And that same antenna was also designed to pick up the lower frequency AM, so in some cases they were a little bit longer than the 2 foot long FM antenna. Your wireless router is much faster in terms of its broadcast speed, operating at 2.4 gigahertz, or if you're talking about a modern day router that can also operate at 5 gigahertz, you need a much shorter antenna to be able to pick that up. So you see an antenna that's typically about 6 inches long on modern day wireless routers. And those may be built into the package, they may be external to that. So let's talk a little bit about the difference between AM and FM. And so your carrier signal will operate at the frequency of the nominal broadcast. So if you're talking about something that is at 750 kilohertz on your AM dial, you see a carrier signal up at the top of your screen. And then you have a modulating sine wave signal, and that modulating sine wave signal mixes with the carrier signal, and you see an AM signal below, which has the carrier signal embedded on top of the information that is being transmitted. Frequency modulation also has a carrier signal, also has a sine wave of data that you wish to mix with it, but what it does instead of changing the amplitude is it changes the frequency. And so as you can see in the bottom drawing there, you have frequency changes despite the amplitude remaining fixed. And so that's just a difference in the modulation strategy of FM versus AM. It's important also, if you're studying electrical engineering, to understand a little bit of the history of how did we get to this point. And so you could take an entire class on wireless communication, but I will just summarize a little bit of the history here of how we got to this point. So James Maxwell, that's an important name that any electrical engineer should know. Maxwell's equations show up in a lot of electromagnetics courses. He was the first one to discover and showcase that electromagnetic waves could propagate through free space. And that happened way back in the 1860s. And that was really pioneering work because it led to a lot of the discoveries that really define our digital world today. So Heinrich Hertz showed that radio wave propagation in a lab could be picked up by antennas. And so he built on the work of Maxwell and showed different antennas can pick up different radio waves. And then Nikola Tesla demonstrated the transmission and radiation of RF energy. That was in the 1890s. And then Marconi invented the wireless radio system, and it was capable of broadcasting a whopping 1.5 miles, which in the late 1890s seemed incredible, but is quite primitive by our modern day standards, where you may be able to receive radio broadcast from dozens of miles away from the station. Continuing on into the 1900s, broadcast radio became very popular. A lot of times you would have families sit around the radio and hear various radio programming in the evenings. And in the late 1920s, research on broadcast television began. And the first television broadcast was actually right in the heart of the Great Depression in 1931. So it was not accessible to many people if you could not afford a television at the time, but that was when the pioneering work of transitioning really our entertainment from radio broadcast to television broadcast began, was in the 1930s. In the 1940s, the first major networks emerged. So CBS and ABC, which are obviously still in existence today, were formed in 1948. So after World War II, many people were able to finally afford television sets and to tune in to the CBS and ABC networks. Back then, certainly they did not have all of the cable networks that we have today. There weren't any 24-hour news networks, and in fact, overnight those broadcast stations would actually shut down instead of showing you infomercials, which may actually be a better approach than we have today. In the early 2000s, high-definition television began to emerge, and so this really started in the Department of Defense realm in terms of surveillance and things like that, and then transferred over into the broadcast area into civilian use as we wanted to get much better clarity of the pictures that we are seeing. In 2009 was the switch to digital broadcast and the end of analog television broadcast, as I mentioned before. So June 12th, 2009 was the day that analog switches were all turned off, and you could no longer get an analog broadcast from over-the-air broadcast networks. 802.11 is an IEEE standard governing Wi-Fi. So I will talk in the next few slides about different wireless technologies and what they're capable of doing. And again, we will also talk a little bit about the history of these things. So Wi-Fi is incredibly pervasive. You can hardly visit a friend's home now without asking what's their Wi-Fi password. So you can get on the network and access your emails or access social media and those kind of things. And that standard really didn't emerge until the late 1990s. And at that time it was still quite slow. And so in the 1990s, we had 802.11a was the first IEEE standard, although some standards started emerging in the late 90s quite a bit before that, in like 1997. And so there we saw broadcast up to 2 megabits per second. But the 802.11 standard really started in 1999 with 802.11a, and that could broadcast at rates of speed between 6 and 54 megabits per second. 802.11b also came out in 1999, and that could broadcast up to 11 megabits per second. 802.11g really improved things in terms of quality of signal, distance the signal could travel, and the speed with up to 54 megabits per second. And then 802.11n in 2009 really was much faster than the technology that existed before. With that, we could get up to 600 megabits per second. 802.11ac, which was known as Wi-Fi 5, emerged in 2012, and that allowed for up to 1.3 gigabits per second on a 5 gigahertz band. So previously we'd only used the 2.4 gigahertz band, and this allowed for a dual band. So within the same home you can actually create with one router a network on 5 gigahertz and a network running on 2.4 gigahertz. 2.4 gigahertz had slower data transmission speeds, only 450 megabits per second compared to the 1.3. But as I mentioned, if you have a larger space, getting on the 2.4 gigahertz allows you to receive signals further out from the router whereas the higher data rate of 5 gigahertz or 5 gigahertz broadcast band, the higher data rate of 1.3 gigabits per second is achievable there. And just last year, 2019, 802.11ax emerged as a new standard, better known as Wi-Fi 6, and that allows for transmission rates of up to 10 gigabits per second. So as people demand more and more bandwidth, we are able to deliver that with better and better technology and better standards, brought to you by the IEEE and their various working groups. It's also important to discuss Bluetooth. So you may use a variety of Bluetooth devices, whether you have a wireless keyboard or mouse, maybe you're using a hands-free headset. That has certainly emerged during the global pandemic. A lot of people using wireless headsets as they're doing various video conferences. And this is also the heart of various in-car communication systems. So if you're trying to stream your music playing from your mobile device into your car, or you want to be able to hear a call hands-free over the audio system in your car, that relies on Bluetooth. Many people also use external speakers to wirelessly broadcast their favorite music. And this allows up to 24 megabits per second transmission. And this creates a personal area network. And various standards have emerged for that, and there have been various improvements. So the newest standards allow you to connect to multiple Bluetooth devices, and they also allow what is known as Bluetooth Low Energy, which allows for a little bit slower connection than some earlier Bluetooth transmission standards, but it does not require nearly as much energy, and so it's very smart about minimizing battery usage, particularly for mobile devices. 802.15.4 is the Zigbee standard. This allows for a range of up to 100 meters, and so you can send things longer than you can with Bluetooth. In many cases, it's a little bit higher power consuming, and this is oftentimes used by hobbyists, and it is popular. XBee is a popular brand of Wi-Fi chip that provides Zigbee mesh. We will also be using XBee chips, but ours will come configured to work with Wi-Fi and an existing wireless infrastructure relying on a router. So, but Zigbee mesh allows us to have communication between various devices. It has a low data transmission rate, up to 250 kilobits per second, but it is very useful for intermittent data retrieval and broadcast. So if you have a sensor network widely distributed, the real advantage here of Zigbee is you can spread things out, especially in an outdoor environment. And if you don't need to send a lot of data, you can send data quite far. So if you're trying to do remote temperature monitoring, if you're trying to collect some information from various remotely placed sensors that are coming at you at a very low data transmission speed, Zigbee is quite useful for that purpose. So speaking of XBee, we will be using XBee Wi-Fi chips in this class. So you see a few examples of the various form factors of XBee chips here. These are a little bit different than the ones that we'll be using. Ours have a little rubber antenna on them. These have, as you can see on the right, a coaxial port that an antenna can be screwed into, and on the left you have a flat antenna that is actually built into the board itself. These rely on serial communication, and we've talked extensively about serial communication in previous lectures. And these XBee radios are fairly low-cost devices that allow us to either create Zigbee mesh networks or to connect to a wireless infrastructure. And depending upon which one you buy, some are designed for Zigbee and others are designed for Wi-Fi. I will get into the pin diagram in an upcoming slide, the next slide, but just so you're aware, there are multiple pins on an XBee Wi-Fi chip, just like any other chip that you might expect, and they can do a variety of things. You can actually perform an analog to digital conversion on some of those pins, and you can also use various serial communication standards, including the USART, which is what we will use in this class. So here is the pin diagram. We will not be using all of the pins on this chip. We will, however, be using pin 1, which is our VCC, that is our power, and that requires a 3.3 volt input, which we won't be able to natively get off of our trainer kit, but we will be able to use a voltage regulator to step down the VDD voltage so that we can use that. We will also be using pins 2 and 3 for our data in and data out, so we can send things back and forth. And we will also need to, on pin 10, connect to ground. Just like almost anything, we will need a ground reference there. And then pin 15 we will use for the associated. What this will actually do is, if it is properly powered, it will turn on. We will connect an external LED to this. It will turn on the LED, and once it is associated with the network that you have programmed it to associate with, it will blink on and off. And so that will tell you that your radio is properly wired and properly associated with the network that you wish to communicate with. These various other pins for analog and digital port I/O we will not make use of in this course, but just so you're aware, there are a variety of applications for these devices that you can use in future projects. In order to use the XBee Wi-Fi chips, they must be configured. So I have pre-configured all of the Wi-Fi chips that I have given you, and at some point they tend to occasionally lose that configuration. So if you were to have some static discharge, that can in some cases wipe out the memory of those chips, so I can actually reflash them with the information that we need. And XCTU is the software that we will use to configure those chips. So I will do a demonstration of that in a live class later on.